Evaluating limits analytically. In section 1.3, we're going to look at basic properties of limits so that we can evaluate limits more efficiently. Basic limits. Let b and c be real numbers, and let n be a positive integer. Property 1. Limit of a constant function as x approaches to any value is equal to the constant itself, which is a b. So look at this example. I have a constant function f of x equal 3. And this function, the function value is always 3 no matter what the x value is. So for example, let's say x is trying to approach it to 2 from both the left and right. What is this function value is trying to reach then? As x approaches to 2 from the left and right, this function value is trying to reach to 3 because it always stays at 3. So limit of this function as x approaches to 2 is equal to 3. Make sense now? Number 2, limit of f of x equal x function as x approaches to c is equal to c. Because this function y is equal to x. In other words, y value and x values are the same for this function. So if x is approaching to c, then y is also approaching to c. So all you have to do is plug c for x, and you will get the limit value. Property 3. Limit of a power function x to the nth power as x approaches to c is c to the nth power. So now you have a y equal power function x to the nth power. So when x is 1, this function will go to the 1 to the nth power. When x is equal to 2, the function value is 2 to the nth power. So when x approaches to c, this function will reach to c to the nth power. So all you have to do again here is to plug c for x, and you will get the limit value. So now let's look at these 3 examples. I have a limit of a constant function 17 as x approaches to 2. So you can envision horizontal line y equals 17. So no matter where x is approaching to, y value always stays as a 17. Therefore, this limit is equal to 17. Now, what is the limit of a function x as x approaches to 2 equal to? Yes, this time you have a y equal x graph, right? So as x approaches to 2, the limit will be same as the where x is approaching to. So the limit of x as x approaches to 2 is 2. This time I have a power function x to the 3rd power. And power function x to the 3rd power as x approaches to 2, it will reach it to 2 to the 3rd power. So limit will be equal to 8. More properties of limits. Let p and c be real numbers, and let n be a positive integer. And let f and g be functions such that limit of f of x as x approaches to c is equal to L, and limit of another function g of x as x approaches to the same number c is equal to k. Then limit a constant multiple b times f of x as x approaches to c is equal to, in this case, you could pull out the scalar multiple b in the front, and you multiply that by the limit of f of x as x approaches to c, which is equal to that scalar multiple b times, and we are assuming limit of f of x as x approaches to c equal a real number L. So since that limit is equal to L, the answer will be equal to the b times L. What if I want to find out limit of f of x plus g of x as x approaches to c? Then that would be the same as limit of f of x as x approaches to c plus the limit of g of x as x approaches to c, which is by hypothesis is equal to L plus k. So you can just add those two limits. Similarly, if it was a difference of f of x minus g of x that we need to find the limit as x approaches to c, that would be equal to limit of f of x as x approaches to c minus limit of g of x as x approaches to c, which is equal to L minus k. And if you want to find the limit of a product of two functions as x approaches to a same number, it would be equal to the product of limits. So that would be limit of f of x as x approaches to c times limit of g of x as x approaches to c, and that would be equal to just L times k. And how about the quotient? Limit of quotient f of x over g of x as x approaches to c is also equal to the limit of f of x as x approaches to c over the limit of g of x as x approaches to c, which is equal to L over k, provided that k is not equal to 0. Lastly, limit f of x to the nth power as x approaches to c. Just you can think that you're using this product rule n many times. So that would be equal to L to the nth power. Example, given limit of f of x as x approaches to negative 5 equals 7, and limit of g of x as x approaches to negative 5 equals 12, limit of h of x as x approaches to negative 5 equals 3. Evaluate each limit. And my first problem is limit of 2 times the f of x minus g of x all over h of x as x approaches to negative 5. So using the properties that we just learned above, this will be equal to 2 times the limit of f of x as x approaches to negative 5 is 7 minus the limit of g of x as x approaches to negative 5 is 12 over the limit of h of x as x approaches to negative 5 is 3, which is equal to 14 minus 12 over 3. So it will be equal to 2/3. How about limit of h's of x to the third power as x approaches to negative 5? Then by last property of a power, this will be equal to 3 to the third power, which is equal to 27. Limits of functions. Limit of a polynomial function. If p is a polynomial function and c is a real number, then limit of a polynomial function p of x as x approaches to c is equal to p sub c. So what it's saying is that if you have a polynomial function, limit of the polynomial function as x approaches to any real number is equal to the function value as you plug c for x. Limit of a rational function. If R is a rational function given by R sub x equal P of x over Q of x, and C is a real number such that Q sub C is not equal to 0, then limit of this rational function as x approaches to C is equal to R sub C, which is equal P sub C over Q sub C, provided that Q sub C is not equal to 0. So again, if you have a rational function and you want to find the limit of that function as x approaches to C, then as long as if it does not make denominator 0, then you can just plug C for x, and that will be the limit value. For example, limit of x squared minus 1 over x minus 1 function as x approaches to negative 1 is equal to, when I plug negative 1 for x, I will get negative 1 squared minus 1 over negative 1 minus 1. And that does not make my denominator 0 since my denominator is negative 2. So then it is okay, and all you have to do is now evaluate this expression. Negative 1 squared is positive 1 minus 1 over negative 2 is equal to 0 over negative 2, which is equal to 0. So the limit of this rational function as x approaches to negative 1 would be equal to 0. Limit of a radical function. Let n be a positive integer. The following limit is valid for all c if n is odd, and is only valid for positive number c if n is even. For limit nth root of x as x approaches to c equal nth root of c. So you know radical functions, when your index is odd, your domain is all real numbers. So it's saying if your index is odd, you can plug any real number c inside of that radical function to find the limit. But when index is even, we can only plug a positive number as an input for radical function. So therefore, if n is even, then you can only plug x equals c as long as c is a positive number. Example, what is the limit of cube root of 22 plus x as x approaches to 5? And because the index is odd, domain of this radical function is all real numbers. It doesn't matter whether the c is positive or negative. I could just plug this for x to evaluate the limit. So the limit of this function would be cube root of 22 plus 5, which is equal to cube root of 27, which is equal to 3. Limit of a composite function. If f and g be functions such that limit of g of x as x approaches to c is equal to L, and limit of f of x as x approaches to L is equal to f of L, then limit of composite function f of g of x as x approaches to c is equal to f of limit of g of x as x approaches to c, and since that is equal to L, the limit value will become f of L. So given limit p of x as x approaches to 1 equal to 3, and limit q of x as x approaches to 3 is q sub 3, which is equal to 10, then limit of q of p sub x as x approaches to 1 would be equal to, according to the property we just learned, this would be equal to q of limit of p of x as x approaches to 1. And that is equal to q of and limit p of x as x approaches to 1 is equal to 3. So this will be equal to q sub 3, and q sub 3 is equal to 10. Therefore, the limit value would be equal to 10. Limits of trigonometric functions. Let C be real number in the domain of the given trigonometric function. Limit of sine x as x approaches to c is equal to sine of c. And since domain of sine x and cosine x is all real numbers, for any real number c, when you try to find the limit of these two functions, you just can simply plug c for x and you will get the limit value. So limit of cosine x as x approaches to c is also equal to just cosine of c. Now tangent x, the domain is all x such that x is not equal to pi over 2 plus n pi for all n element of integers. So as far as c is not equal to pi over 2 plus n pi, you can plug c for x, and therefore limit will be tangent of c. What would it be the limit of cotangent x? The domain of cotangent x is equal to x such that x is not equal to n pi, where n is element of any integers. So as far as c is not equal to n pi, you could also plug c for x, and the limit will be cotangent of c. The domain of cosecant x is equal to x such that x is not equal to n pi and n is element of integer. So therefore, limit of cosecant x as x approaches to c, as far as c is not equal to n pi, you could plug c for x and limit will be cosecant of c. Domain of secant function is same as domain of tangent x. So this will be equal to x such that x is not equal to pi over 2 plus n pi, where n is element of integers. So as far as c is not equal to pi over 2 plus n pi, you can just plug c for x and you will get the limit secant c. Example. What is the limit of sine square x as x approaches to pi over 3? As you know, domain of sine x is all real numbers. So therefore, all I have to do to evaluate this limit is that I just need to plug pi over 3 for x and then square it. So this will be equal to sine of pi over 3, and then whatever the value is, you just need to square that. And sine of pi over 3 is equal to radical 3 over 2. So you're going to square that and you're going to get 3/4. What is the limit of tangent x as x approaches to 5 pi over 4? Is 5 pi over 4 in the domain of tangent x? Yes, it is. So therefore, I could just plug 5 pi over 4 for x, and my limit value will be equal to tangent of 5 pi over 4, and tangent of 5 pi over 4 is equal to 1. How about limit x times cosine of x as x approaches to 2 pi over 3? Domain of cosine x is all real numbers, so I can plug 2 pi over 3 for x, and limit of a product is a product of a limit. So 2 pi over 3 times cosine of 2 pi over 3, which is equal to 2 pi over 3 times cosine of 2 pi over 3 is negative 1/2. And when you multiply these two fractions, we need to cross cancel. So these two and these two cancel. Positive times negative is negative. I get negative pi over 3. Find the limit by factoring and canceling. If the limit of f of x as x approaches to c cannot be found directly, but let's say there is another function g of x such that f of x is equal to g of x for all x in the open interval containing c except at possibly one point at x equals c, and limit of g of x as x approaches to c exists, then the limit of f of x as x approaches to c has to be equal to limit of g of x as x approaches to c. So it sounds very hard, but if you look at this example, it will make more sense. So look at this example right now. Limit of quantity x squared minus x minus 6 over x plus 2 as x approaches to negative 2. According to what we learned before, if we have a rational function, as far as it does not make my denominator 0, I just could plug c for x and evaluate the limit. However, as you see, if I were to plug negative 2 for x here, you can see that denominator is 0. So that will make it undefined. And not only that, if you look at the numerator, it is negative 2 squared minus negative 2 minus 6 over negative 2 plus 2. And the numerator, I get 4 plus 2, which is 6, minus 6, which is 0. So I get 0 over 0. So from the algebra review, you know this function has a hole at x equal negative 2. If I factor the numerator, this function is equal to limit x approaches to negative 2. If I factor the numerator, two numbers whose product is negative 6 and sum is negative 1 is negative 3 and positive 2. So this rational functions factors like this. So you can see how I have a common factor x plus 2 top and bottom. So if I cancel this just become a line. However, this will be a line with a hole at x equal negative 2. So we are calling this as a new function g of x. We're calling this function original f of x. So we're saying this x squared minus x minus 6 over x plus 2 function and this new g of x function, which is just a line x minus 3. These two functions are exactly the same everywhere except at x equal negative 2. Because this function is a line with a hole at x equal negative 2, and this function, it is just a line without a hole. So according to the text above, these two functions are same everywhere at except one point. To find the limit of this is the same as finding limit of this. To find the limit value, function value does not has to exist. As far as if you have x approaching, as long as there is a point such that as x approaches to c from the left and as x approaches to c from the right, those both function value are approaching to the same y value, then that is called the limit L. So that will be this case. So now you cancel the x plus 2 and evaluate the limit of x minus 3 function instead as x approaches to negative 2. Now you can plug negative 2 for x. Limit is negative 2 minus 3, which is equal to negative 5. So we found the limit. Let's do another problem. So let's say I want to find the limit quantity x plus delta x squared plus quantity x plus delta x minus 5 minus quantity x squared plus x minus 5 all over delta x. So you can see if I plug 0 for delta x, then I get x squared plus x minus 5 minus x squared minus x plus 5, which is 0 over 0. So again, this limit cannot be found directly. So what you needed to do is multiply out and hopefully factor the numerator. And after dividing out technique, you can plug 0 for delta x, therefore find the limit of this expression. So limit delta x approaches to 0. I'm going to multiply out quantity x plus delta x squared to a perfect square trinomial. So this is equal to x squared plus 2x delta x plus delta x squared. I'm going to distribute the plus, which doesn't change anything. So that will be plus x plus delta x. I have a minus 5 there. And I'm going to distribute the negative 1 to all these three. So now you have negative x squared minus x plus 5 over delta x. So I can see that positive x squared and a negative x squared is 0. I have a positive x and negative x is 0. And negative 5 plus 5 is 0. And what's left is 2x delta x plus delta x squared plus delta x, which has a delta x as a common factor. So I'm going to factor out the delta x in the front, so I can divide out by delta x in the denominator. So now I have limit delta x approaches to 0. I'm going to factor out delta x, open, then I get 2x, I get plus delta x plus 1 over delta x. So now you can see you have a common factor, delta x and a delta x. So you can divide that out. And now you get to plug 0 for delta x. Now all I have is 2x plus delta x plus 1. So now as you plug 0 for delta x, my limit becomes 2x plus 1. So you found the limit, and your limit is 2x plus 1 function. Third one, limit of 2x over quantity x minus 4x squared as x approaches to 0 is equal to, again, if you do direct substitution for 0 for x, I plug 0 here, I get 0. 0 minus 0 gives me 0. So I cannot just plug it in. So when that happens, well, numerator is monomial, so you can leave it the way it is. And the denominator has a common factor x, so you can factor that out, and you will have 1 minus 4x. So then now you can cancel the common factor x, and this limit is equal to limit 2 over 1 minus 4x as x approaches to 0. And these two functions are exactly the same except at one point x equals 0. So now you can plug 0 for x, and you get to find the limit. And limit is 2 over 1 minus 4 times 0, which is 2 over 1, which is 2. So you found the limit value. Next example, again, if you were to plug 0 for x, I do get 1/4 minus 1/4 on the numerator, which will give me 0. And 0 for x will give me 0 in the denominator. So again, direct substitution wouldn't work to evaluate this limit. And this does not factor either on the numerator nor denominator. So what do we do here? So what you have here is complex fraction. So if you have a complex fraction, go ahead and simplify the complex fraction by getting rid of any denominators on the numerators or any denominators in the denominator. Then you can do the direct substitution after you simplify the complex fraction. So to simplify the complex fraction, I want to get rid of denominators on the numerator, which is x plus 4 and 4. So your technique for simplifying complex fraction is multiplying top and bottom of a complex fraction by LCD. So LCD here in this case is 4 times x plus 4, and you will multiply by quantity 1 by multiplying numerator by 4 times x plus 4 and multiply denominator by also 4 times x plus 4. So you can see it will not change any value of this rational expression at all since you multiplied by quantity 1. However, now by distribute 4 times x plus 4 to the first expression, x plus 4 will cancel, so you get 1 times 4 on the numerator, which gives you 4. Now, secondly, you will multiply this expression by second expression, which is negative 1/4. Then this time, 4 and 4 will cancel, so you will have minus 1 times x plus 4, which is x plus 4. Now you multiply denominator with the denominator, so you get 4 times x plus 4 is what you have. So now you are going to distribute the negative on the numerator and simplify the expression. So you have a limit for minus x minus 4 over 4x times x plus 4. So then 4 minus 4 is 0. My expression become limit negative x over 4x times x plus 4 as x approaches to 0. And now you can see I have a common factor x top and bottom. So you can cancel that out. So then your expression finally become limit x approaches to 0 of negative 1 over 4 times x plus 4. So then now you can go ahead and do the direct substitution, 0 for x, and that would give you negative 1 over 4 times 0 plus 4, which is equal to negative 1 over 4 times 4 is 16. So you found the limit value. Next example, limit of x cubed plus 1 over x plus 1 as x approaches to negative 1 is equal to, and as you can see again, negative 1 cubed is negative 1. So if I do direct substitution, negative 1 for x, I will get 0 over 0. And this one is a sum of cubes which factors. So as we learned in previous page, we will go ahead and factor the numerator, and we will divide out the common factor, and we will do the direct substitution for negative 1 for x to evaluate the limit. So note that sum of cubes factors as a cubed plus b cubed equals a plus b times quantity a squared minus ab plus b squared. So now apply that to x cubed plus 1. 1 is 1 cube. All right, your x is a, your b is 1. So if you factor that out, you will get limit as x approaches to negative 1. Factor, you get x plus 1, x squared minus x plus 1 over x plus 1. So now you can see again, you do have a common factor, x plus 1, x plus 1. So you can cancel that. So the original limit will have the same limit as you apply limit x approaches to negative 1 to x squared minus x plus 1 function instead. And you will get negative 1 squared minus negative 1 plus 1, which is 1 plus 1 plus 1. So limit value is 3. The last special technique to evaluate limit when direct substitution doesn't work is the rationalizing technique. Find a limit using a conjugate. So it is called the rationalizing technique. If f of x is a rational function containing a radical and limit of f of x as x approaches to c cannot be found directly, try multiplying f of x by 1 in the form of conjugate of either the numerator or denominator over itself. And then find the limit of the new function instead. Because all you have done is multiplying the expression by 1, so it's not going to change the value of the limit, but rather it changes the different form where direct substitution is possible. So look at this example. First example, I have a limit quantity 1 minus radical x over quantity x minus 1 as x approaches to 1. And if you plug 1 for x, I get 1 minus 1, which is 0, over 1 minus 1, which is 0. So as you see, direct substitution doesn't work. And I only have a radical on the numerator. So you can multiply conjugate of 1 minus radical x, which is 1 plus radical x. And do the same to the bottom so that you have multiplied the original expression by quantity 1. So you're not really changing anything. However, by doing so, now my function will look like limit as x approaches to 1. A minus b times a plus b is a squared minus b squared. And I do have x minus 1 times 1 plus radical x in the denominator. And if you simplify the numerator, that is equal to 1 minus x over x minus 1, 1 plus radical x. But what do you know about 1 minus x and x minus 1? Yes, they're opposites. What happened? You have a 3 over negative 3. Do you leave it like that or do you simplify? Yes, we do simplify and call that negative 1. Same thing. If you have a 1 minus x and x minus 1, they are opposites. If I rewrite the numerator, it is minus x minus 1 over x minus 1. So these does cancel and you will get a factor negative 1. So when you notice that they are opposites, I don't even necessarily asking you to rewrite that as a negative of parentheses x minus 1. You can just cancel the common factor that is opposite, and all you have to do is making sure to write the negative 1 factor on the top. So now this is equal to limit x approaches to 1 of negative 1 over 1 plus radical x. So now you get to plug 1 for x, and your limit is now equal to negative 1 over 1 plus radical 1, and radical 1 is 1, so you get negative 1/2. So you found the limit. Now let's look at the second example. I have a limit of quantity radical 2 plus x minus radical 2 over x as x approaches to 0. So again, to find this limit, you are going to multiply by conjugate of numerator since that's where radicals are. And conjugate of radical 2 plus x minus radical 2 is radical 2 plus x plus radical 2. So you're going to multiply exactly the same thing in the denominator so that it is quantity 1. So now this will be equal to limit x approaches to 0 of a minus b times a plus b is equal to a squared minus b squared. And in the bottom I have x times radical 2 plus x plus radical 2. And when you square them, you get 2 plus x minus 2 over x times radical 2 plus x plus radical 2. So then plus 2 minus 2 is gone, and I have x over x. So x over x is a common factor, so you can also cancel them, and you will have a factor 1 on the top. So now this function finally become 1 over radical 2 plus x plus radical 2. And now you get to plug 0 for x, and that will be 1 over radical 2 plus radical 2. So the answer is 1 over 2 radical 2. And you can simplify this by multiplying top and bottom by radical 2. So your answer is radical 2 over 4. So your limit is radical 2 over 4. Let's do one more. Limit quantity radical x plus 1 minus 2 over x minus 3 as x approaches to 3. Again, you will multiply it by conjugate, and conjugate of radical x plus 1 minus 2 is radical x plus 1 plus 2 over radical x plus 1 plus 2. So when you multiply numerators, it becomes a square, which is radical x plus 1 square minus 2 square. And in the bottom, you have x minus 3 factor, and you have another factor, radical x plus 1 plus 2 factor. And when you multiply that out, you get limit x approaches to 3 of x plus 1 minus 2 squared is 4 over x minus 3 radical x plus 1 plus 2. And you can see that your numerator now become x minus 3. And you do have x minus 3 factor in the denominator, so that you get to cancel them. So this become limit x approaches to 3 of 1 over radical x plus 1 plus 2. So now you get to do the direct substitution. You get 1 over radical 4 plus 2, which is 1 over 2 plus 2, which is 1/4. So you found the limit. Squish Theorem. Assume f of x less than equal to g of x less than equal to h of x for all values of x near c, except possibly at c. If the limit of f of x as x approaches to c is equal to limit of h of x as x approaches to c, and they're both equal to L, then the limit of g of x as x approaches to c is equal to L as well. So you can see from this picture, we have these three functions. H of x have a higher value than g of x, except at x equals c, they do have same function values. And g of x has a higher function value than f of x for all x except at one point at x equals c. So that we do have this inequality going on. Now let's say limit of f of x function as x approaches to c is L, and limit of h of x function also have the same limit value as x approaches to c, then the middle function g of x as x approaches to c has to have the same limit value, since the highest and lowest have the same limit. That makes sense, right? So in a way, limit of g of x as x approaches to c got sandwiched in between two functions, one that is higher than g of x and one is lower than g of x. So the squish theorem is also called the sandwich theorem. So it's pretty easy to understand, and application is easy as well. And I will definitely put that on the first exam, so make sure you know how to do it. Once you see how to do one, it's pretty easy. So example, suppose that negative x squared plus 8x minus 13 function is less than or equal to f of x function, which is less than or equal to x squared minus 8x plus 19 function for all x. Find the limit of f of x as x approaches to 4. And you might wonder, where is f of x? They didn't have to tell you. All you have to do is really show this statement right here. Find out limit as x approaches to 4 of left-hand side function, and also find out the limit as x approaches to 4 of right-hand side of f of x function. And if they are equal, then by Squish Theorem, limit of f of x as x approaches to 4 has to be the same as the limit of those two functions. So first of all, I'm gonna find the limit of negative x squared plus 8x minus 13 as x approaches to 4. And this is just a regular polynomial. We know we can find the limit by direct substitution of 4 for x. So the limit would be negative 4 squared plus 8 times 4 minus 13, which is equal to negative 16 plus 32 minus 13, which is equal to 3. Now, how about limit of highest function, which is x squared minus 8x plus 19 as x approaches to 4 would be equal to, again by direct substitution, I have a 4 squared minus 8 times 4 plus 19. It's a 16 minus 32 plus 19, which is again positive 3. And because lowest function and highest function both have a limit value as x approaches to 4 is equal to 3, then the middle function, thus by Squish Theorem, you make sure you say that on the test so that you are arguing by a known theorem. Thus by Squish Theorem, limit of f of x as x approaches to 4 must be also 3. And that will be your conclusion. Two special limits involving sine and cosine. Limit of sine x over x as x approaches to 0 is equal to 1. Limit quantity 1 minus cosine x over x as x approaches to 0 is 0. These two special limits came from use of unicircle and the Squish theorem. So here is how the first limit came from. We chopped off a quarter of unicircle. Since it's a unicircle, it's a circle of radius 1. You know that every point on the unicircle is cosine of theta, comma sine of theta, where theta is the angle from the standard position. So given the picture we have right now, you can see the largest portion of a triangle, which is right now colored with green, of course, has a bigger area than the area of a sector, which is now colored in blue, which is a part of a unicircle. And that area is slightly bigger than the area of a triangle inside of that sector. So now let's try to write out what is the area of each of this colored region. So first area of largest triangle is 1/2 times base times height. And base is 1 since it is unicircle. I don't know the height, but if you call this a height, the tangent of theta is opposite over adjacent, and opposite is h right now, and adjacent is length 1, so that will be 1. And you can see that since h over 1 is h is equal to the tangent theta, and that's where this height came from. So you can see that area of a green region is 1/2 times 1 times tangent theta. Now, area of a blue region, you learned this from trigonometry, and area of a sector is 1/2 r squared theta, and theta in radian. But radius is 1, so right now we have 1/2 times 1 squared times theta. Area of a red triangle, again, since it's a triangle, area must be 1/2 times its base times its height. And this one, since it is acute triangle, height is from the highest point come to the base with a 90-degree angle. So this is the height. And as you saw, we pointed out that this point right here is cosine theta, comma sine theta. So height of this length is sine theta. So the height is sine theta for this red triangle. Therefore, area of this red region will be 1/2 times base 1 times height sine theta. So now when you simplify, I get tangent theta over 2 greater than equal to theta over 2 greater than equal to sine theta over 2 is what we have now. And we can multiply everybody by 2. And because 2 is a positive number, it will not change the inequality. So we can multiply by 2, and that will give us new inequality. Tangent theta is greater than equal to theta, which is greater than equal to sine theta. I still want to find out what is the limit of sine theta over theta. So I got a little bit of more ways to go. And tangent theta, though, can be rewritten as sine theta over cosine theta, as you know, which is greater than equal to theta greater than equal to sine theta. And now you can divide everybody by sine of theta. So when you divide by sine theta, and you divide by sine theta, and divide by sine theta, and since we are looking at the theta in the first quadrant right now, so sine theta is positive, so it will not change the inequality. And now you have 1 over cosine theta greater than equal to theta over sine theta greater than equal to 1 is what you have. The limit of a function that we want to find out is sine theta over theta. So now we need to flip over and change the inequality. Note that half is greater than third, obviously, right? But when we make a reciprocal, 3 is bigger now. So when you have an inequality, and if you are going to make reciprocal for both, you need to switch the inequality symbol. So now when we make a reciprocal for all 3, this will become cosine theta, but now inequality symbol needs to change it to opposite side. Sine theta over theta. I need to change inequality to opposite side. And 1 is 1 over 1. When you flip over, it's still 1 over 1. So we have still 1 on the right hand side. We couldn't really find out what's the limit of sine theta over theta as theta approaches to 0. Because direct substitution will cause me to get sine of 0 over 0, which is 0 over 0. This is why we had to do all this work to figure it out. What is the limit of sine theta over theta as theta approaches to 0 is? So now we're going to apply Squish Theorem. So limit theta approaches to 0 of cosine theta is, we can do direct substitution here. So this will go to cosine of 0. And cosine of 0 is 1. And the limit of a constant, theta approaches to 0, limit of a constant function is the constant itself, as we learn. Thus, by Squish Theorem, limit theta approaches to 0 of sine theta over theta equal 1 as well. Second special limit limit 1 minus cosine of x over x as x approaches to 0 equals 0. This one too, we use the same background with this unit circle. We're going to use a Squish Theorem. So let's say we have all this so far, and we got here where we have a cosine theta less than equal to sine theta over theta less than equal to 1. And this is where we're going to start because there's no reason to go over all over again the same thing. So let's just say we are here, okay? So then we are going to multiply all three sides by sine theta. So when you multiply by sine theta, all three sides, I get sine theta cosine theta times by sine theta and multiply sine theta to 1 as well. So what I have now is sine theta cosine theta less than equal to sine square theta over theta less than equal to 1 times the sine theta is sine theta. Again, because theta is in the first quadrant, sine theta is positive, and therefore we will not change the inequality symbols. Now from Pythagorean identity, sine square theta plus cosine square theta is equal to 1. So sine square theta then is equal to 1 minus cosine square theta. So we are going to replace this for sine square theta there. So now I have sine theta cosine theta less than equal to 1 minus cosine square theta over theta less than equal to sine theta. And 1 minus cosine square theta is difference of squares. So it factors as a minus b times a plus b. So sine theta cosine theta is less than equal to, you factor the numerator, I get 1 minus cosine theta times 1 plus cosine theta over theta less than equal to sine theta. And you can see I'm trying to find the limit of 1 minus cosine theta over theta. So if I can just get rid of 1 plus cosine theta factor in the middle, it will give me desired expression that I want to find the limit of. So we are now going to divide all three sides by 1 plus cosine theta, 1 plus cosine theta, 1 plus cosine theta, so that these cancel. So now I do have 1 minus cosine theta over theta, which I want to find out what the limit was. So now you have sine theta cosine theta over 1 plus cosine theta less than or equal to 1 minus cosine theta over theta less than or equal to sine theta over 1 plus cosine theta. So now to find the limit of 1 minus cosine theta over theta as theta approaches to 0, I'm going to use a Squish Theorem. So let's find the limit as theta approaches to 0 of sine theta cosine theta over 1 plus cosine theta. We're going to do the direct substitution and replace 0 for theta. I will get sine of 0 times cosine of 0 over 1 plus cosine of 0. And sine of 0 is 0, cosine of 0 is 1 over 1 plus 1, which is equal to 0 over 2, which is 0. And limit of sine theta over 1 plus cosine theta as theta approaches to 0 by direct substitution, I get sine 0 over 1 plus cosine 0, which is equal to 0 over 1 plus 1, which is 0. So by Squish Theorem, the limit of 1 minus cosine theta over theta as theta approaches to 0 is equal to 0. Now we're going to take a look at some examples that use these two special limits that we just learned. Note that the argument of the trig function must exactly match the denominator in order to apply the special limit property, meaning this input of your sine function has to be exactly the same as your denominator in order for you to say this limit is equal to 1. And it is actually this 3, but let's say if as x goes to 0, 5x goes to 0 as well. As x goes to 0, 3x goes to 0 as well. So you don't necessarily have to fix this part, but make sure that input for sine and the denominator matches exactly. So does this limit. Input for cosine function and the denominator has to match in order for use this property. So here is an example. Limit sine of 5x over x as x approaches to 0 equal to, I see students who's pulling out this 5 in front of the limit. What we learned in the past is that limit x approaches to 0 of c times f of x is equal to c times limit of f of x as x approaches to 0. So these two are equal. It is true. But what's not true is that limit of f of cx as x approaches to 0 is not equal to c times the limit x approaches to 0 of f of x. So if you're pulling that 5 out, you are doing this right now, which is not true. So you cannot pull that 5 out. So then what do? You just said input has to match with your denominator, but they don't match. So again, we will do a little bit of algebraic manipulation. You can multiply this expression by quantity 1, but since you do need the 5x in the denominator, you will multiply by 5 over 5. And you're going to multiply this 5 with the denominator, but this 5 now is 5 times the sine of a 5x. It is constant multiple. So you could pull that 5 out to the front, no problem. So that would be equal to 5 times limit sine 5x over multiply 5 and x. Now you have a 5x as x approaches to 0. And as I told you, as x approaches to 0, 5 times x also goes to 0 as well. So now we get to use special limits, and you can say that then this limit is equal to 1, and therefore this is equal to 5 times 1, which is equal to 5. Next question. Limit of tangent x over x as x approaches to 0. Well, we don't have that property, right? Those two special property only involves sine and cosine. So of course, what we need to do here is change tangent x. So we're going to rewrite this as limit tangent x is a sine x over cosine x, and you already had a factor x and have a cosine x as x approaches to 0. So now you can see this expression is really sine x over x times 1 over cosine x. So we are going to rewrite that as that product, limit x approaches to 0 of sine x over x times 1 over cosine x. And limit of a product is product of limits. So I have now limit x approaches to 0 of sine x over x times limit x approaches to 0 of 1 over cosine x. And this now you can use the property that we learned today, which is 1. And the other one, you can do direct substitution, since the cosine of 0 is not 0. It is actually 1. So you have a 1 times 1, which is 1. Let's keep going. What is the limit of 1 minus cosine theta over 3 theta as theta approaches to 0? Well, we have to have this argument and the denominator matches exactly. in order for us to use this theorem, right? But this time, that 3 in the bottom is not an input of a function. It is 3 times theta. It is really constant multiple. So you can pull that out in the front. So make sure you understand which one can be pulled out and which one cannot. And since the 3 is in the denominator, that will be 1/3 times limit 1 minus cosine theta. I pulled out 1/3, so you only have a theta now as a theta approaches to 0. And now that looks exactly same as what we have on the box. So therefore, this will be equal to 1/3 times, what is this limit? 0. So you have 0. How about limit of 1 minus cosine square x over x as x approaches to 0? Yes, this is again difference of squares. So yes, you can factor. So this is equal to limit, factor the numerator, I get 1 minus cosine x, 1 plus cosine x over x as x approaches to 0. And again, this part right here is the special limits that we know. So you can change this to product of limits, and this is a limit x approaches to 0 of 1 minus cosine x over x times limit x approaches to 0 of 1 plus cosine x. And the first part of the limit is the special limit, and you know this is 0. Second part, we can do the direct substitution, so we get 1 plus cosine of 0, and cosine of 0 is 1, so it is 0 as well.